Hello everybody. In this video, we will explore Newton's laws of motion and learn how they can be applied to the motion of celestial objects. As we saw in the previous video, Kepler's model worked so well and Galileo so successfully countered the remaining objections to the heliocentric model that by the mid-1600s, scientists were nearly unanimous in accepting the validity of Kepler's laws of planetary motion. However, no one knew why the planets move in elliptical orbits with varying speeds. This all changed in 1687, when Isaac Newton published his famous book called Mathematical Principles of Natural Philosophy. In this book, he laid out precise mathematical descriptions of how motion works in general. Today, these ideas are described as Newton's laws of motion. But before discussing Newton's laws of motion, let's explore some fundamental concepts and questions. The first one is why objects like moons and planets move at constant velocity if no force is acting on them. The answer to this question is conservation of momentum. As we saw from Galileo's experiments, objects in motion tend to remain in motion unless a retarding force will make them stop. But Galileo did not explain why that happens. Today, we know that this happens because of conservation of momentum. The total momentum of interacting objects cannot change unless an external force is acting on them. These interacting objects exchange momentum through equal and opposite forces. The same idea applies to objects moving in a circular or rotational motion. In this case, the angular momentum, the rotational equivalent of linear momentum, is the one conserved. The angular momentum is calculated as the mass of the orbiting object times its velocity times the radius of its orbit. Since a planet orbiting a star or a satellite orbiting a planet has no net external torque, its angular momentum is constant. Because a planet orbiting a star has constant angular momentum, a change in one of the variables will cause the others to change as well, so that momentum is conserved. In this example, because the radius, the distance between the planet and the star, is reduced without changes in the mass of the planet, the velocity of the planet has to change so that momentum is conserved. As a result, when a planet travels along an elliptical orbit, its speed reduces when it's further away from the star and increases as it approaches the star. The reason why a planet speeds up when it's close to the star is the same that explains why a figure skater rotates faster when she brings her arms in. This reduction in the radius will result in an increase in her rotational velocity. The opposite is true when she opens her arms. The radius increases and so the velocity decreases. But what is the original force that gave our planet its original spin? The force that produced the initial motion was the formation of the solar system. We'll discuss the nebula theory on chapter 4. This initial energy is conserved because there are no external forces either slowing down or speeding up Earth's rotation. Energy can be transformed, but cannot be created or destroyed. This principle is known as conservation of energy. There are two categories of energy that are important in astronomy. One is gravitational potential energy, which is energy a physical object has in relation to another massive object due to gravity. The other is the potential energy from mass itself. The famous equation from Albert Einstein relates mass to energy. Let's now explore Newton's laws of motion. You should already be familiar with the first law of motion, also known as law of inertia. This law states that if there is no net force acting on the object, then the object will maintain constant velocity. If that velocity is zero, then the object will remain at rest. Newton's second law of motion pertains to the behavior of objects for which all existing forces are not balanced. The second law states that the acceleration of an object is dependent upon two variables: the net force acting upon the object and the mass of the object. Forces and accelerations also have a direction. In other words, accelerations are in the same direction as the applied forces. If equal forces are applied in opposite directions, the net force is zero, and the object will move with constant velocity. Newton's third law of motion states that for every action or force in nature, there is an equal and opposite reaction. So, if object A exerts a force on object B, then object B also exerts an equal force on object A. Notice that the forces are exerted on different objects. All three laws apply to planetary motion. For example, celestial objects, including planets, are always changing the speed and direction of their motion. So why do they change the speed and direction? They are responding to an applied force. And what force is that? These changes in the intensity and direction of motion happens in response to the force of gravity. The force of gravity can be expressed mathematically through Newton's universal law of gravitation. Three simple statements summarize this law. Every mass attracts every other mass through the force called gravity. The strength of the gravitational force attracting any two objects is directly proportional to the product of their masses. For example, doubling the mass of one object doubles the force of gravity between the two objects. The strength of gravity between two objects decreases with the square of the distance between their centers. For example, doubling the distance between two objects weakens the force of gravity by a factor of 4. So let's put these concepts together. The gravitational force is the attractive force between any two objects with mass higher than zero that are separated by a distance. So, does the apple fall towards the earth, or does the earth move towards the apple? In fact, they both move towards each other. Both apply an equal force to attract the other object. So, if the forces are equal, will they cause equal acceleration? From Newton's second law, we know that a force is the product of mass and acceleration. So acceleration is inversely proportional to the mass. As a result, if the mass is higher, the acceleration will be smaller. Since the mass of the Earth is much, much higher than the apple, it is the apple that accelerates towards the Earth. So, how do we quantify the gravitational force? Consider two objects of mass A and B. The distance between the center of mass is considered the distance between the two objects, not the distance between the surfaces. Assuming the mass of object A is m1 and the mass of object B is m2, and that the mass of A is bigger than the mass of B, the law of universal gravitation states that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of their distance. We can combine these two statements into this equation. So if the mass of any of the objects increases, the gravitational force increases. The gravitational force is directly proportional to the product of their masses and inversely proportional to their distance. Relating the gravitational force, the mass of, and the distance between objects is the gravitational constant, g. The value of the gravitational constant is the same throughout the universe, and it was calculated in 1798 by Henry Cavendish. Newton's law greatly expanded the scope and extent of Kepler's law. They apply to all orbiting objects, and the orbital paths can have many shapes. By combining Newton's and Kepler's laws, we can measure the masses of distant objects, an incredibly powerful tool that today is being used to explore stars and planets well beyond our own. The new understanding of motion unlocked by Newton's law of universal gravitation also allowed us to send rockets and probes into space. It also allowed us to understand natural phenomena that greatly impact our lives. We learned some fundamental concepts in physics that help us understand how gravity affects the motion of celestial objects. Conservation of angular momentum keeps a planet rotating and orbiting the sun. Celestial objects get the energy from the original contraction of the solar system, and this energy is transformed and exchanged as these objects interact through gravity. The strength of the gravitational force attracting any two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Newton's law greatly expanded the scope and extent of Kepler's law. They apply to all orbiting objects, and the orbital paths can have many shapes. By combining Newton's and Kepler's laws, we can measure the masses of distant objects, send probes and spacecraft into space, and understand natural phenomena that greatly affects our lives. Thank you for watching, and I see you in the next video.